Hello friends. The Sun, a massive star at the center of our solar system, holds many mysteries that scientists are still trying to fully understand. One of the most fascinating phenomena related to the Sun is the flipping of its magnetic field, an event that occurs approximately every 11 years. This event is part of what is known as the solar cycle or sunspot cycle, which influences space weather and has effects extending all the way to Earth. At the core of the Sun, nuclear fusion produces vast amounts of energy, primarily in the form of light and heat. This process also generates magnetic fields, which are complex and constantly changing. The Sun's magnetic field extends far beyond its surface, into the solar system, in what is known as the heliosphere. These magnetic fields are generated by the movement of electrically conducting fluids inside the Sun, a process similar to how Earth's magnetic field is generated. As the Sun goes through its cycle, the magnetic fields wind up, twist, and tangle due to the differential rotation of the Sun, meaning the equator of the Sun rotates faster than the poles. This complex movement leads to increasing magnetic activity and the formation of sunspots, which are cooler, darker spots on the Sun's surface caused by interactions with magnetic field lines. Approximately every 11 years, the buildup of magnetic energy reaches a peak, known as the solar maximum, characterized by a large number of sunspots and intense solar activity such as solar flares and coronal mass ejections. These phenomena can send streams of charged particles into space, sometimes directed towards Earth, affecting satellites, communication systems, and even power grids. The most intriguing part of the solar cycle is when the Sun's magnetic field completely flips. The magnetic North Pole switches to the south and vice versa. This reversal happens at the peak of the solar cycle. Scientists monitor this flipping closely because it is a crucial indicator of the level of solar activity and helps predict future solar behavior. Understanding when and how the Sun's magnetic field will flip involves observing sunspots and measuring the magnetic fields at various points on the Sun's surface. Space missions like NASA's Solar Dynamics Observatory and the Parker Solar Probe provide scientists with data necessary to analyze these changes. For the current year, predicting whether the Sun's magnetic field will flip involves looking at the progression of the solar cycle. Scientists use historical data and current measurements to estimate the timing of the next flip. As of now, if we are nearing or at the solar maximum, there might be a magnetic flip soon. However, these predictions are always subject to revision as new data comes in. The Sun's magnetic field is generated by the movement of plasma within its interior, a process known as the solar dynamo. Plasma inside the Sun moves in complex patterns due to convection. That means heat-driven movement where hot plasma rises, cools, then sinks back down, and the Sun's rotation. This movement of conductive plasma generates electric currents, which in turn produce magnetic fields. The Sun rotates faster at its equator than at its poles. This differential rotation stretches and twists the magnetic field lines over time. Imagine a baker twisting a strip of dough. Similarly, the Sun's rotation twists the magnetic field lines around its axis. This twisting creates complex loops and whirls in the magnetic field, which are visible as sunspots on the Sun's surface. Sunspots are indicators of strong magnetic activity. They appear darker because they are cooler than the surrounding areas on the Sun's surface. The temperature difference is due to intense magnetic fields that inhibit the normal flow of hot plasma from the Sun's interior to its surface. The number of sunspots varies over approximately an 11-year cycle known as the solar cycle. This cycle ranges from solar minimum with few sunspots to solar maximum, with many sunspots and intense solar activity. At the solar maximum, the Sun's magnetic field is highly twisted and complex. The poles then undergo a reversal where the north and south magnetic poles switch places. This flip is part of the natural cycle of solar activity and resets the magnetic field strength. After the flip, the field gradually untangles itself, moving towards another solar minimum. The flipping of the sun's magnetic field has significant implications for space weather. Events like solar flares and coronal mass ejections are more frequent during periods of high solar activity. Solar flares are intense bursts of radiation coming from the release of magnetic energy associated with sunspots. CMEs are massive bubbles of gas threaded with magnetic field lines that are ejected from the sun's corona, the outermost part of the solar atmosphere. Both solar flares and CMEs can have profound effects on Earth, including disrupting GPS signals, causing power outages, and affecting the safety of astronauts. Monitoring the solar cycle helps predict these events and mitigate their impact on modern technological systems. Scientists observe these phenomena using space-based telescopes like the Solar Dynamics Observatory and the Parker Solar Probe. These instruments provide high-resolution images of the sun's surface and measure various properties of the plasma and magnetic fields. For instance, helioseismology, the study of vibrations on the sun's surface, allows scientists to infer details about the sun's internal structure and the movements within. Other stars also exhibit magnetic cycles, though the length and characteristics of these cycles can vary significantly from our sun's. For instance, many red dwarfs have much more intense magnetic activity compared to our sun. They often exhibit stronger and more frequent stellar flares that can completely envelop the star. Comparing these stars to our sun can highlight the diversity of stellar magnetic phenomena and explain why these differences might occur based on the star's sizes, ages, and internal structures. A type of neutron star with an extremely powerful magnetic field, magnetars demonstrate what happens when stellar remnants cool but retain an intense magnetic field. They are known for emitting strong bursts of X-rays and gamma rays, which are thought to result from shifts and cracks in the crust due to magnetic stress. By comparing magnetars to the sun, viewers can appreciate the scale and power of magnetic fields across different stellar environments. The planets within our solar system also present a variety of magnetic phenomena that can serve as a good contrast to the solar magnetic cycle. Earth's magnetic field flips, though much less frequently than the sun's, approximately every 200,000 to 300,000 years. This comparison can help explain the role of fluid dynamics within both the Sun and Earth in generating magnetic fields and what causes these fields to eventually reverse. Jupiter has the strongest magnetic field among the planets in our solar system, which is thought to arise from metallic hydrogen inside Jupiter's core. Discussing Jupiter's magnetic field can introduce concepts of how different materials inside planets and stars contribute to magnetic field generation. The solar wind, a stream of charged particles ejected from the sun's atmosphere, shapes the heliospheric magnetic field, which is the magnetic field that fills the solar system. This comparison highlights how the sun's magnetic field not only flips, but also dynamically interacts with and shapes the space environment of the entire solar system. Comets have tails that point away from the sun, formed by the solar wind interacting with comet material. This phenomenon can be used to illustrate the influence of the sun's magnetic field on other bodies in the solar system and how magnetic fields can have visible effects on celestial objects. The history of observing the sun dates back to ancient civilizations, which often revered the sun as a deity. Ancient Chinese, Greek, and Egyptian astronomers made regular solar observations, noting phenomena like sunspots, although they did not understand their nature or implications. The earliest known records of sunspots were made by Chinese astronomers around 800 BC. The invention of the telescope in the early 17th century marked a significant advancement in solar observation. Galileo Galilei, one of the most famous astronomers, used a telescope around 1610 to observe sunspots directly. His observations challenged the then prevailing view of the celestial realm as unchangeable and perfect. suggesting instead that the Sun was a dynamic body with its own anomalies. In the 19th century, the study of the Sun became more systematic with the establishment of dedicated solar observatories and the development of spectroscopy. Scientists like Joseph von Fraunhofer and Norman Lockyer began analyzing the Sun's spectrum, which led to the discovery of new elements such as helium and provided insights into the Sun's composition. The identification of the solar cycle's periodicity by Heinrich Schwabe in 1843, who noted a roughly 10-year cycle in the number of sunspots, laid foundational knowledge for understanding the Sun's magnetic activity. The Maunder minimum, a period from about 1645 to 1715, when sunspots became exceedingly rare, highlighted the Sun's influence on Earth's climate. This period coincided with the Little Ice Age in Europe and North America, where colder temperatures were recorded, suggesting a link between solar activity and climate changes on Earth. The 20th century brought significant advancements with the development of space-based solar observatories. The launch of Skylab in the 1970s and later the Solar and Heliospheric Observatory and the Solar Dynamics Observatory provided unprecedented views of the Sun from space, free from the distortions of Earth's atmosphere. These missions have been crucial in observing the Sun's surface, its atmosphere, and phenomena such as solar flares and coronal mass ejections in great detail. George Ellery Hale in the early 20th century first linked magnetic fields to sunspots, showing that sunspots were regions of strong magnetic activity. The concept of the solar dynamo, how the Sun generates and maintains its magnetic field through the motion of conducting materials within it, was developed throughout the 20th century. The theory helped explain the solar cycle's regularity and the periodic flipping of the magnetic field. Today, the prediction of solar cycles and magnetic flips is based on a combination of observational data, theoretical models, and computational simulations. Researchers continually refine these models based on data from newer missions like the Parker Solar Probe and the upcoming missions planned to study the Sun further. The flipping of the Sun's magnetic field is a natural and expected part of the solar cycle. It plays a significant role in the dynamics of the solar system and can have profound effects on space weather impacting Earth. Understanding this phenomenon is crucial for preparing for and mitigating its effects on our technology and communication systems. If you liked this video, please like, comment, and share the video, and please do not forget to subscribe for more videos.